In problem number 2, let me consider a quadratic factor. All right. So let's say you have been given with unity feedback open loop transfer function, unity feedback open loop transfer function, something like k into 1 plus 0.5s divided by s into 1 plus 2s into 1 plus 0.05s plus 0.125 s squared. All right. And the question is draw the Bode plot and determine gain margin and phase margin. All right. See, yesterday's problem was pretty lengthy. It took about 1 hour 40 minutes to complete that particular problem. That's because I have, it is as good as solving 2 problems. So yesterday's problem had 2 parts. The first part was to find out gain margin and phase margin, and the second part was something like determine the value of k for a given gain and phase margin. So you'll have to consider that particular problem as separate, 2 problems. All right. So very important yesterday's problem. So as this, because you are dealing with a quadratic factor. Now, first of all, what you have to observe from the given open loop transfer function is that whether the given transfer function is expressed in time constant form or not. Okay. Now, if you look closely, you can see that the given open loop transfer function is expressed in time constant form. You can see 1 plus s into t divided by 1 plus s into t. And you can also observe that the quadratic factor is also being kept in time constant form. 1 plus st, right? Plus t into s squared. Okay. So you can directly write that g of s is in time constant form. Okay. So that's your step 1. Step 1. And in step 1 itself, you can determine the corner frequencies. Okay. So corner frequencies as in the reciprocal of the time constant. So reciprocal of, let's say, this factor. Okay. So this is omega equal to 1 by 2 or 0.5 radian per second. Okay, and then you have the corner frequency. Okay, this is omega c, and the corner frequency of the numerator factor is 1 divided by 0.5. So that's 2 radian per second. All right. So yeah, this doesn't have any corner frequency, so you can just put a dash, okay, because there is no time constant associated with the factor which is lying at the origin. Okay, it could be whole at origin or 0 at origin. So this is done, this is done. Okay, what about this, the quadratic factor? How will you find the corner frequency of quadratic factor? Other day I have told you that corner frequency of quadratic factor is nothing but the natural frequency of oscillation, right? So first you have to, extract the natural frequency of oscillation. So what you can do is you can just rewrite the quadratic factor. Okay. And equate it to 0. Rewrite the quadratic factor and equate it to 0. So what do we have? We have 1 plus 0.05s plus 0.125 s squared is equal to 0. Now I should be able to compare this quadratic factor with the standard equation, right? So what is standard equation of a second order system? It is s squared plus 2 zeta omega ns plus omega x squared is equal to 0. So somehow I should convert my given quadratic equation into the standard form. So that can be done by taking out 0.125 outside the bracket. So if we keep 0.125 outside the bracket, what do we get? We get a square plus 0.05 divided by 0.125. Okay. 0.05 divided by 0.125. That's 0.4 plus 1 by 0.125, that's 8, is equal to 0. Right? Now you compare the coefficient. So what you get is omega n square, you will get it as 8. So omega n square is equal to 8, or omega n is equal to under root 8, which is 2.83 radian per second. So that is the corner frequency of quadratic factors. So the same, method holds good for if a factor is found in the numerator. So either it is a quadratic pole or quadratic zero, you can always extract omega n using this method. All right. So let's write down. So the corner frequency of this quadratic pole is 2.83 radian per second. All right. So once we have the corner frequencies, you can go ahead with the magnitude table, right? So in magnitude table, systematically you will have to arrange the factors. Okay. Now, before actually constructing the magnitude table, let's put S is equal to j omega in g of s. Okay. So that will convert the given open loop transfer function into frequency domain. So g of j omega, I'm sorry. So g of j omega is equal to k into 1 plus j 0.5 omega divided by j omega into 1 plus j 2 omega into you have 1 okay, s square becomes j omega whole square, so that becomes negative 0.125 omega square. So this I can write it as 1 minus 0.125 s square is j omega the whole square, so minus omega square. All right. So that's my real part, and the imaginary part going to be j 0.5 omega. Okay. So that's my transfer function in frequency domain. Okay, so this is my real part, and this is my imaginary part. All right. So fine. Now we are good to go for the magnitude table. So let me write the next step as the magnitude table. For a while, let me retain this transfer function. Let me later erase it. So magnitude table. Now, while constructing magnitude table, what you have to do is you have to arrange the factors systematically. So first, let us take the column name as factor, followed by corner frequency, and followed by individual slope, and then the net slope. Okay, so let me write the equation for net slope. Net slope is previous plus current slope. So previous slope plus current slope. All right. Now let us start listing out the factors over there. So let's start with the very first factor, which is having the lowest frequency, right? So you have to arrange the factors in the ascending order of the corner frequency. So the first factor is pole and origin. Yeah, one thing I forgot to mention that you are supposed to draw the Bode plot with k equal to 4. All right, so please include that in the question. So you're supposed to draw the Bode plot with k equal to 4. That is what is given. So when you say k is equal to 4, in the numerator you will have this. Okay. So we can separate out the factors. So this is going to be my first factor. So normally what I'll do, I'll club that k along with the factor which is present at origin. It could be 4 or 0. All right, fine. So this is my first factor, which I can write it something like 4 divided by j omega. All right. And what is the corner frequency of this factor? Actually, the corner frequency is 0 because this is nothing but pole at origin. But 0 you cannot consider in Bode because you get 20 log of 0 as infinite. Hence, let us start with a small corner frequency of 0.1 radian per second. So that's something like the starting point of our Bode. Okay, again I'm repeating, it need not be 0.1, it can be 0.01 or 0.001. Okay, just that if you take very, very low frequency, your Bode plot is going to expand. Okay, so 0.1 normally you can say the rule of thumb, it generally works well. All right, fine. The individual slope. So I have a pole at origin. So individual slope is minus 20 decibel per decade. Therefore, the net slope becomes minus 20 decibel per decade because there is no previous history. Okay, fine. Let me keep it over there. Okay, and let me draw the remarks sometime later. Fine, next factor. Okay, so next factor is probably this, right? This is 0.5 radian per second. So this is the lowest factor. What is it? This is first order pole. So 1 divided by, that is this 1 divided by 1 plus j to omega, whose corner frequency is 0.5. Okay. And it's a first order pole, hence the individual slope contribution is minus 20 decibel per decade. Then what do we have? After 0.5, we have the greater frequency as 2 radian per second. So this is found in the numerator, and this is nothing but your first order 0. So j 0.5 omega. So it's a 0, first order 0, with a corner frequency of 2 radian per second. All right. So what is the individual slope contributed by first order 0? You know that zeros always contribute positive slope. So it is plus 20 decibel per decade. Okay. And finally, you have this, the quadratic pole, right? So quadratic pole is 1 divided by, what did we get? We get 1 minus 0.125 omega square plus j 0.5. Whose corner frequency is 2.83, right? And the individual slope, it's a quadratic pole, right? So quadratic pole as in the order is 2, right? So it is 2 times 20 decibel per decade. Since it is a pole, hence negative. So quadratic pole contributes a slope of minus 40 decibel per decade. All right. Once that is done, you can start filling up the next steps. Right? So for the first factor, net slope is minus 20 decibel per decade. Hence, draw a straight line with minus 20 decibel per decade from 0.1 radian per second to the next corner frequency. So from 0.1 to 0.5 radian per second, you should draw a straight line with a slope of minus 20 decibel per day. But we haven't evaluated what is the magnitude of the Bode diagram at the starting frequency. So you can find out M. M is equal to 20 log mod of 4 by omega. And what is omega? Omega is 0.1. So at omega equal to 0.1. So that is 20 log 4 minus 20 log 0.1. So find out 20 log 4 minus 20 log 0.1. Log 4 is 12 decibels minus 20 log 0.1. So it's about 32 decibels. So put together you will get 32 decibels. So basically your magnitude plot starts from 32 decibels with a straight line of minus 20 decibels per second, drawn from 0.1 and it will end at 0.5. Okay, so that's your first. So 32 decibels. I will erase this and I will just write M is equal to 32 decibels. Now let's come to the second factor. What do we have? Minus 20. So your next slope becomes previous slope, right? So previous slope is minus 20 plus current slope is minus 20. So next slope becomes minus 40 decibel per second. Previous is minus 20, current is minus 20. So minus 40 decibel per second. So you need to draw a straight line having a slope of minus 40 decibel per decade from 0.5 to straight line with a slope of minus 40 decibel per decade from 0.5 to 2 radian per second. So that is the second factor. Okay. Third factor, well, we have the individual slope as 20 decibel per decade, due to which the next slope becomes previous slope. What was your previous slope? Is minus 40 plus the current slope. What is your current slope? Plus 20. So the next slope becomes minus 20 decibel per decade, right? Minus 20 decibel per decade. So that you need to draw a straight line with a slope of minus 20 decibel per decade from 2 radians per second to 2.83 radians per second. You can say draw a line with a slope of minus 20 decibel per decade from 2 to 2.83 radians per second. Done. And finally, we have the last factor. Okay. So the next slope we need to calculate. So previous slope is minus 20 plus the current slope, which is minus 40. So the next slope becomes minus 60 decibel per decade. So you have to draw a straight line with a slope of minus 60 decibel per decade from 2.83 to where is the terminating point? There is no terminating point. So infinity you can write. So from 2.83 radian per second onwards, the straight line keeps on moving with a slope of minus 60 decibel per decade till infinity. So just you draw a straight line with minus 60 decibel per decade slope. Right. So that's your magnitude table. Later we'll have to put it into Bode diagram. That we can do it little later. But we quickly take an image of this. So that same thing I can include in the notes. All right. Next up, we have the phase diagram. So quickly let us construct phase table. So angle phi. So phi is equal to, you have to write the equation. You have factor 4. Whenever you have a real number, with zero imaginary part, the angle becomes 0. So whenever you have k, you can just take the angle as 0. So we have a pole at origin, right? Pole at origin. So this pole at origin will give you a phase angle of minus 90. And then we have just to be in line with numerator angle and denominator angle. Let me start with the zeros. So what do I have? I have numerator angle as tan inverse of y by x. So that is 0.5 omega. 0.5 omega is the imaginary part and real part is 1. So basically imaginary by real will give you 0.5 omega. Minus 90 degree. The tan inverse of omega by 0 gives minus 90. Minus 90 is due to the pole angles. And then we have minus tan inverse of 2 omega. Tan inverse of 2 omega. And then we have minus tan inverse of the real part is 1 minus 0.125 omega square, and then you, sorry, it should have been other way around. 0.05 omega 1 minus 1. So that's our phase angle equation. This is our phase angle. As you can clearly observe that many terms are dependent on frequency. For example, this term, and this term. So what happens is that as you start varying the frequency, the net angle of the system is going to vary. But this is not so straightforward. It's not that you take frequency variation from 0 to say 10,000 radian per second and keep on correcting the angle. No, it is slightly different from previous problem due to the presence of quadratic factor. Okay, now you must have observed this in trigonometry that when you have a complex number of the say type x plus iy, right? So whenever you have a complex number of this kind x plus iy, so what happens is that your angle phi varies from 0 to 92. So that means to say, it is one quadrant operation. Okay, I'm not saying first quadrant or second quadrant or third quadrant. I'm just saying one quadrant operation. Okay, that is nothing but like the angle 0 to 90 degree lies in one of the quadrant. Okay, so that holds good for terms such as this 1 plus 0.5 omega, 1 plus j 2 omega, etc., etc. Okay. However, if you look at the quadratic factor, quadratic factor, such as this. The order is 2, right? Because the typical equation follows s square plus 2z omega ns plus omega n. So what happens in quadratic factor is that the angle varies from 0 to 180 degree. 0 to 180 degree. So this is very, very important. So quite often what happens is that you put this particular equation in your calculator and you start varying the omega value, and whatever calculator gives the angle, you will start substituting. No, you are not supposed to do that, because whenever the quadratic factor comes into picture, you must understand the fact that the system angle is not changing from 0 to 90 degree. It is in fact changing from 0 to 180 degree. So therefore, for a quadratic factor, correction factor needs to be introduced. Okay. So this holds good for quadratic pole as well as quadratic zero. That's the reason I have just mentioned quadratic. Okay. Now, why is it? If you look at your calculator, okay, the calculator will have a logic to determine the tan inverse of imaginary part by real part. So this calculator is built with a logic to determine the angle between 0 and 90 degree. So it cannot determine the angle which is lying between 0 and 180 degree. That's the reason you will have to manually, correct the equation whenever this quadratic factor comes into picture. Okay. So for a quadratic pole, add minus 180 degree in equation 1. Okay, so let's say this is our equation 1. Okay. So for a quadratic pole, add minus 180, and for quadratic zero, that is if s square plus z omega n s plus omega n square is present on the numerator, add plus 180 in equation 1. From omega n onwards. From omega n onwards. Okay. This is very, very important. From omega n. That means to say, everywhere you don't have to add. When that factor comes into picture, that time you have to start adding either minus 180 degree or plus 180 degree, depending upon the value of natural frequency of oscillation. That's because if you look at, let's say, frequency as 0.5 radian per second, at 0.5 radian per second, the quadratic pole doesn't come into picture, right? The quadratic pole comes into picture only at omega n is equal to 2.83 radian per second. So till 2.82, you don't have to add the correction factor. The moment you increase the frequency beyond omega n, you add either minus 180 degree or you add plus 180 degree. I'll tell you how to do. Okay, so that's very, very important. That's the important step. If you can understand this particular step, you can say Bode plot is done. All right. Now let us construct the data. So this is your angle phi, and this is your omega. This is your omega. So let's start varying the frequency. Let's say 0.1, 0.5. Okay. So what I have taken, let me write that. And let's say 2. right? And I won't take 2.83 because 2.83, what happens is that you will end up in getting an infinite dimension. So 2.84, 2.84, and then 10, some 100, and some. Oh, you can take different frequencies. Now, let us divide this frequency into two parts. For frequencies from 0.1 to 2, you can say that omega n doesn't come into picture, right? So omega n comes into picture beyond this frequency, right? Because omega n is 2.83 radian per second. So what you can do is for frequencies greater than omega n, so here you can write that omega is greater than omega n. So add minus 180 degree. So whatever angle you get, you go on adding minus 180. And this is phi. Okay. So this phi you can obtain directly from equation 1. Okay. And when you add the two angles, you will get a net angle. Okay. So remember one thing, you need to add correction factor only from frequency which is greater than omega, that is from 2.84 radian per second onwards. Okay. So frequency is less than omega n, you don't have to bother, just you substitute omega and just write down the angle phi. So this you will get it as minus 98, minus 98.73, and the second one you will get it as minus 122.22, and at 2 you will get it as minus 132.27. Okay, so at 2.84 you will get it as close to minus 210 degree, and then two seventy. This time. So this is your phase state. Phase state. So once that is done, you can go ahead with whatever. If you have any doubts, you please ask. If not, I can go ahead with the Bode. So this is important. See, I have written also. You have to add the correction factor only for frequencies greater than omega. Today I'll scan and circulate them. Alright, so let's go ahead with the Bode diagram. Let's see what kind of Bode diagram we are going to get. uniform y-axis because you have linear scale along y-axis. So this is your decibels. Okay, the magnitude is expressed in decibels, and this is your angle phi in degree. Okay, this is your angle phi in degrees. So this is your 0 degree line. This is plus 20, plus 40, plus 60, minus 20, minus 40. This is minus 180, minus 150, minus 120, minus 90. Angles are increasing. It is in the increasing sense. This is minus 210, minus 240, minus 270. So we have written the y-axis scale. Next up, we have the decades. First decade, second decade. All right. Once you are done with that, you can draw the reference slope lines. Right. So 20 decibel per decade, we want minus 20 decibel per decade. Why minus 20, minus 40? You can refer magnitude plot. So in the magnitude plot, we see that we need to draw minus 20 decibel per decade line, minus 40 as well as minus 60. Do we need any plus 20 decibel per decade line? Any positive slope lines do we need? No, right? We don't want any positive slope lines. Hence, I'm not going to draw the positive reference line. But still, since it is just problem number 2, let me also tell you how to draw positive slope. So this is your positive slope. This is plus 1. Plus 1 means 20 decibel. This is minus 1. That is minus 20. Minus 40. Minus 3. Minus 60. Okay. Once you are done with this, what you do is find the magnitude at omega equal to 0.1, right? So, yeah, we have to even mark the frequency, right? So this is your starting frequency, 0.1. Then the decade of it will become 1, then 10, 100, 1K, 10K, so on and so forth. Okay. So your x-axis is nonlinear scale, and decade variation in frequency is achieved along x-axis. All right. So at 0.1, how much did you get the magnitude as? You got the magnitude as 32 decibels. Right. So this is 32 decibels. And now you refer the magnitude plot. So starting from 32 decibel, draw a straight line with a slope of minus 20 decibel per decade from 0.1 to 0.5 radian per second. So you need to identify 0.5 radian per second. So 0.5 going to be the exact half of this. Okay. So I'll write here 0.5. So let me do it. This is my reference minus 20 decibel per decade. So from 32 dB, I will draw a straight line. Which is having a slope of minus 20 decibel per decade. So this is my minus 20 decibel per decade line. Once that is done, you can go to the second factor. Now at the second factor, the net slope becomes minus 40 decibel per decade. So you have to draw a straight line having a slope of minus 40 decibel per decade from 0.5 radian per second to 2 radian per second. So 2 radian per second approximately somewhere here. And right here, 2 radian per second. And what should be the slope? Minus 40. So for minus 40, you can take the reference line and then start drawing the same. So till here, that is minus 40. So I write down then from 2 to 2.83 radian per second, the net slope becomes minus 20 decibel per second. So we need to determine 2.83. So 2.83 will be somewhere here. So this is 2.83. So the net slope becomes minus 20 decibel. Done. And then from 2.83 onwards, the net slope becomes minus 60 decibel per decade. So take the reference line minus 60 decibel. So this is minus 60 decibel. Okay, so that's the magnitude plot. Starting from 32 dB, the straight line will have minus 20 decibel per decade till the next corner frequency, which is located at 0.5 radian per second. And then from 0.5 radian per second, the first order pole comes into picture, due to which the net slope becomes minus 40 decibel per decade. And at 2 radian per second, first order 0 comes into picture, hence plus 20 should be added to the previous slope, hence becomes minus 20 decibel per decade. And from 2.83 onwards, already pole with a slope of minus 40 decibel per decade comes into picture, due to which the net slope becomes minus 60 decibel per decade. So this is the magnitude plot. So once the magnitude plot is done, you can go ahead with the phase plot. So phase plot at 0.1 radian per second, we have close to 99 degrees. So 99 is somewhere here, right? And then at 0.5 we have 122 degrees. So 0.5 is exactly half of this. 122. And then at 2 minus 132. 2 minus 130. Somewhere here. And then 2.83, it is around 207. Somewhere here. And then at 10, 275. 260. Right at 10. And then at 100 and 1000, it is 270. Now you join the phase plot. Your phase plot. Once you are done with phase plot, you can determine phase crossover frequency omega PC and gain crossover frequency omega. So phase crossover frequency, it is between 2 and 2.83. So if you draw the graph in a graph sheet, you will get 2.6 radian per second. So here let me write omega PC is 2.6 radian per second. And omega GC, you will get it as is between 1 and 2, right? So around 1.4 radian per second. Radian per second. So once you have the omega PC and omega GC, you can find the gain margin. Okay? So to find the gain margin, what you do? Draw an extension line from omega PC towards the magnitude plot. And this particular distance gives gain margin. So gain margin is somewhere about 7.6 dB. Remember, which is positive because this gain margin is found below 0 decibel line. Once you are done with gain margin, you can go ahead with phase margin. So phase margin, what you do? From gain crossover frequency, draw a line vertically downwards. And the point at which the line cuts with the phase plot will help you in getting the phase margin. So this is phase margin. So with respect to scale, we have to carry out the measurement. So phase margin is about 51 degrees. Okay, let me write the scale also. So scale, what I have done is x-axis, 1 unit is equal to 1 decade. 1 unit is equal to 1 decade, and then now along y-axis, what we have done is 1 unit we have taken as 20 decibels, and we have also taken 1 unit as 30 degrees.